Welcome to the next episode in a video series where I'm sharing some tips and tricks on Arduino programming and specifically having a bit of a look at how I've done a few things in my mini lathe customization project. Now the response to my last video was a little bit tepid, unfortunately, with about 90 views. I had 9 likes, that's about a 10% like rate, which is not that bad, but really not getting much traction. Honestly, it takes me about 3 or 4 days to put together a video like that. So it's not really my favorite thing to make either because I'm not actually learning anything. So if I can't really get any good traction, then I might need to reconsider the direction of this video series. But in any case, let me try again with this video and see how we go. In this video, I'm going to show you a way to do some simple multitasking. It can be used for things that are not super mission critical or time critical. But if your code is tight, you usually can maintain an accuracy of around about under, say, 5 milliseconds. I think it's pretty good enough for most sort of background little operations. It's not also guaranteed, so you want to make sure that your code can really cope with having a bit of a hiccup or missing an event or something like that. It will actually reschedule itself and restart the schedule in some certain situations. So yeah, you wouldn't want to be depending on it fully. But for things like flashing an LED or getting some data or updating a display or checking some buttons or something like that, something that's not that critical, it's more than good enough. So in the mini lathe, I'm actually using it to check the button actions, getting some values from the system, and then updating the display. I'm also doing that system state check for the automatic shutdown and warning, updating the power display, fan speed control and temperature data information, and also updating the display for that. So you can sort of see these things are all happening in that manner. And you can see that the timings look the same, like 50 milliseconds, 100 milliseconds for the system check, power update display 250 milliseconds, fan control every half a second. So that seems a little bit weird because you think they'd all be happening at the same time. But what I actually do is when I start the schedule, I have an offset so that each of them don't start on the exact same millisecond. So they're 5 milliseconds or so offset. And that means that they basically have their own little chunk of 5 milliseconds free processing time to go ahead and perform that function. And so they won't actually impact or delay each other when they're actually operating. And that actually leads to a more seamless and consistent result for the end user. And that's what I'm really trying to achieve with this scheduling. It's a very consistent and real-time feel to the interface. If you're using Windows and you click something and you have to wait a little while and then you click something and the response is slow, it's not a good interface sort of feel. And when we're dealing with embedded devices, I think everyone should be trying to achieve a result that is much better than an operating system like Windows environment, something where you press and always feel confident you're going to get an immediate result. I mean, that's one of the things that I feel is important in any case. Now, really, this scheduling system is super simple. There's nothing complex, no complex classes or objects or timers or things that you can't see. This is a very, very straightforward way of implementing it, and that's why I like it, basically. Don't get me wrong, I use timers and interrupts and all those things when it's important, but the more you layer on those things that are hidden and occurring in the background, the more difficult it is to sort of debug and really understand and manage your code. So, do that stuff when it's necessary, but don't do it when it's not necessary, and that's one of the policies that I take as well. So in this example, what I'm going to do is I'm just going to be scheduling 4 activities to turn on and off 2 different LEDs. So one activity to turn on this red LED, which I've got on port A4, and turn it off again for another activity, and turning on the blue LED and turning it off again. So there's going to be 4 scheduled events. It's a very simple sort of demonstration, and it's not all that meaningful. It's not really the point of being meaningful, but it's just to demonstrate how all of these interactions occur independently and gives you the result that you need. So whether this be an LED or some other sort of activities in your program, you can mix it up and change it up as you see fit. Alright, so for those of you that have not already skipped ahead, let's stop the waffle here and let's get into some of the code. So I've got my clean project here. The first thing I'm going to do is set up a couple of values to actually track those scheduling timing values. And I'm just going to copy and paste here to save you some time because I've got this already prepared on the side here. So we have these 4 values, and each of them will hold the schedule time or the time in millis where the action should occur. And then we will have 4 initial values. So when the values are initialized, what the scheduling offset should be. So in the case, for example, of the red LED, it will be switched on without any offset. So once the schedule is initialized, it will immediately go, and it will be switching off in 500 milliseconds. So that means that effectively this is controlling the duration of the switch on time, half a second. For the blue LED, will be coming on in 1 second and will turn off at the 2-second point. I hope you're following me so far. And then we have the value that is added each time the action occurs. So every time, for example, this action occurs, it will be scheduled to occur a certain amount of time in the future. And in this case, it's going to be 1500 milliseconds. And as obviously the red LED on and off states are actually something that are synchronized in time or going forward in the same timeline, we have to add the same amount. Obviously, if these were all independent activities, you wouldn't add the same amount, or you might or you may not. But specifically in this case, we want to have that relationship, that 500 millisecond offset relationship maintained, because that's the duration that the on time is on. And so we'll add the same amount. So every 1.5 seconds, we will get 500 millisecond flash, and every 2.5 seconds, we will get the blue LED flashing. Now you'll notice that the times are such that the amount they're added are not the same amount. If they all added by 1500, then the flashing times would occur in the same synchronous timeline, but this is actually added by 2.5 seconds, so it's going to slowly fall out of sync and behind. And I think that's what I want to demonstrate with these values, to show that these values are not synchronized. What's happening on the blue LED and what's happening on the red LED is independent of each other. Next up, we're going to define which I and O ports we're going to use, all very standard Arduino stuff, so nothing surprisingly amazing there. I'll put in my normal divider here. Alright, here's my setup. So setup, nothing very special going on here. We will just set up those I/O values. Red LED and blue LED, A4, A5, set up as outputs, and this is going to be a negative logic environment. In other words, you have to pull it to low to turn the LED on, so I'll initialize those as being high. Alright, then we're getting into the main loop. And in here, we won't do anything yet. I'll get rid of this bit of garbage. I'm not interested in that. Put another subsection in here for all the scheduling routines. And the first thing we're going to do is we're going to initialize the schedule, have a routine to initialize the schedule. That just sets up all of these variables to their initial state. I'll just copy and paste this to save some time here. Well, this is a quick episode maybe. There's nothing surprising in here. When the init is requested, it passes the current time value in millis. I could have just used the millis value within this subroutine as well, but I'm giving the option to externalize that, so if there's some reason you want to customize that value, it can be done. And all that's being done is that each of the schedules on off are set to their relative initialized value added onto the current millis value. So in other words, the current time plus the initial delay time will be when it first comes on next round. And I have one other value, which is to track if initialization was requested, and I'm going to put it in here as well. So we need to define that, and what it is, it's a special value, a logic control value for the scheduling, which says an initialization has been requested. It provides the ability to demand a initialization request in certain circumstances. The first time we run, we want it to initialize, so I'm going to set it as true straight off the bat. Obviously, once we do the initialization's been done, so I'm going to clear that initialization request within this routine here, just like that. So this assumes that the initialization was called somewhere, so therefore the initialization request is no longer required. You clear that, and then setting up all of those initialization values. And then we have one more subroutine which I'm using to adjust the schedule value. So after you do the action, you want to adjust to the next one. Not entirely unnecessary routine, but it does a few other bits and pieces in here, so I'm using it this way. Fundamentally, all we're doing is taking that original value that was provided and adding the provided value to add. That's really all it's doing. Then all we need to do is return that value as well. So that in itself seems like a pretty useless routine, but there's a little bit more to what I'm doing here than just this. There's a safety mechanism that I'm adding, which is why I have this routine. So this safety mechanism is pretty simple. All it's really doing is providing a way to make sure that the schedule is not falling way too far behind. It can happen in some circumstances that you're actually falling out of the window of the current time, because we're just adding this value onto the original value, so we're incrementing over time. But if for some reason your actual millis got way far ahead of the value, you're going to actually have to add on these values a lot of times before you actually catch up to the current time schedule. So this safety mechanism just detects that situation where the current millis values has gotten so far ahead and resets it. So it looks like this. So all we're saying is that if the value millis, which is the current time provided here, is greater than the value original after it's been adjusted. So it's been adjusted, so in theory value millis the current time should be way before the current value. It should be waiting to schedule this event. But if we're ahead, then that's probably a non-nominal situation. But it's probably recoverable in most situations if it's not too far ahead. But if it is ahead, then it does a secondary check, so and, which means, well then, if the value millis minus the original value is greater than 600, so 600 is the millisecond value that I'm using to say, if you're more than 600 milliseconds behind, then you've really got a problem and we have to resync the situation or reinitialize the situation. So the reinitialization is pretty straightforward. All I'm doing is setting up for a schedule initialization. So schedule init request equals true. That'll force a resync for all of those time values and probably offset the schedule as it was running, but it's already upset anyway, so it doesn't really matter. And since this value original was so far out of whack, it's useless in any case. It just immediately sets some sort of somewhat logical value. It's a bit messy, but it doesn't matter. In any case, it's going to schedule a init request, so soon enough it's going to solve the problem anyway, so this is not that critical, this second action. So that's it. So as I said, in the simple light, the schedule adjust doesn't seem like a necessary routine, but the necessity is this safety mechanism there. So let's get to the most important thing, which is running the actual schedule. At the head of the routine, I'm actually checking for that schedule initialization request. So if the schedule initialization request is there, then it's going to initialize the schedule, which is a good action. But I also have something else that it checks for as well, which is that if the values millis is less than the last millis, so there's this value which I haven't added yet, which is the fact that every time this runs, it will save this the last time it ran, the last millis it ran. And in theory, value millis should always be going forward, but millis has a limited scale. I think it rolls around or runs out of capacity every, I think it's 2 or 3 days in an Arduino. It might vary on different platforms. In any case, 2 or 3 days or something like that, and the values millis will roll over, and so therefore it's going to go and be less than what the last time you ran, and that's going to be a problem for the schedule as well, for executing the schedule, because it's looking for forward movement. But obviously if millis goes backwards, there's not going to be any more forward movement, so that's going to be another case where the schedule needs to be reinitialized. And obviously each time we run, we need to say the last time we run, so that's something else we do in this routine. And we haven't actually created this sched last millis, or the last time it run value, so we better do that as well. Add that up the top here. Yeah. So these are the two really global control logic values that we have. Alright, so that's basically all the logic structure in place. Now we're actually getting into executing individual schedules, which are all in here. And I'm just going to add the red one first, and we'll take a quick look at that. So there's the red one. The action is very straightforward. It just says that if the value millis, and the value millis is being provided. Now again, with value millis, I could have just hard-coded it in here as millis, but I'm giving the ability to have an external provided value, so in case it's being manipulated or something like that. In any case, the value millis has exceeded the schedule time. It could be greater than equal, but anyway, greater than the schedule time. Then it's going to do the action. And the action, in this case, is to turn the LED on. And this is reverse logic, so it turns it to low, not high. So this is the key action here. That's for actually doing what you want. Now, you could write a more complex routine if you want it in here, and assuming that it was maybe under 5 or 10 lines, it's probably okay to do it in here as well. I think if you're looking at more than 5 or 10 lines, then you're better off making a separate subroutine for the action, so in order to keep your code a little bit more readable and manageable. I mean, if there's 1,000 lines in this one action section here, this whole schedule schedule execute routine is going to be extremely difficult to follow. Not impossible, but definitely don't recommend trying to stick everything in here if it's huge. But in a lot of the cases, you're already going to have a subroutine there, or it's going to be a concatenation of a few little subroutines, so you probably can do it in here. And in a lot of the cases of the mini lathe, that was the case. I think in 8 or 9 of the cases, only one of them I externalized as a separate subroutine. So yeah, so that's on for the LED, and obviously for the off state, it's pretty much exactly the same, except looking at the different variables, the schedule off values, get off, add, and obviously we're not turning the LED on, we're turning the LED off. And then for blue, it's going to be exactly the same. So we'll just add those in here, save you the boredom. So there's the blue, and this time we're looking at blue on, and blue on add. For the blue on, we're turning it on with the reverse logic. The off is there as well. So that's everything. So in this case, we have 4 scheduled actions with an offset start time and a specific frequency of execution. Probably important to note that the way that this logic works means that things will always be locked to the common timeline. So it's never going to fall out of the timeline. It doesn't matter how long these individual actions take to execute, the timeline will still be protected. So in that sense, it's pretty accurate as far as maintaining frequency of execution. Alright, so let's run this code. Obviously, we're not actually running the code here, so we need something in the loop here. So for this demonstration first, what I will do is simply execute the main events. Here we go. Alright, so this is where we're actually executing the events, or executing the schedule, and obviously this loop is just continuously looping around here. And every time I execute the schedule, or attempt to execute the events in the schedule, I'm providing the current millis. Let's see if that compiles. All looking good, so let's download it. And there you have it. You can see the LEDs are doing their own thing. Now you can see that the timing is not locked between the red and the blue LEDs. They're doing their own things independently. And if I just reset this for a second, I'll hit the reset here, you'll see that the blue LED takes a little, the red LED comes on straight away, but the blue LED is delayed in the startup by whatever it was, 1.5 seconds or whatever I put in there. Ready? 3, 2, 1, go. Red, blue, blue. So how do we use this in a practical application? I mean, it's all very good. We have this sort of loop here, but how will we practically use it? Now, as I said, in the mini lathe, I used it a little bit differently. I'm actually using it in the main, say, execution or running time, or when the lathe is spinning. But that's not really the only way you can use this. So I'm going to show you a quick way to use this practically, maybe in your application. As you know, we use the delay function of Arduino quite often to delay certain things. So what I'm going to do is I'm going to make a little custom delay routine, and I'm going to rename it as wait. So this is the routine that I probably recommend that you use if you're interested, to replace the delay routine. What happens is you put the amount of milliseconds you want to wait for. Once the routine enters, it's going to capture the current millis, and then it's just going to loop until that amount of millis has been exceeded with a small delay of 1 millisecond in each. And then inside this main loop here, we also are doing that run schedule execute. So it's a way of combining your delay routine that you would normally use and replacing that with this wait routine, and that wait routine will always do your background tasks. So you can always, wherever you put your wait in or your delay in, you're going to have those background tasks being executed or checked. So in that case, instead of doing what we did before, we would just use this wait routine in the main loop somewhere, and so it looks something like this. And if we program that, of course you can see it's exactly the same thing. So again, this doesn't seem all that meaningful. So what we're going to do is we're going to take this and we'll stick this into the application we made in the last lesson, the one where we're doing that menu. So let me get that set up and then I'll bring you back. I need to get the buttons on here so we can actually have that menu functioning. And what we'll do is we'll combine the code and actually have this LED flashing going on in the background while we're operating that menu at the same time. Alright, let me get to it and I'll bring you back. Alright, so I've got the buttons plugged back in there like we had last time. Let's get that menu going and see how that goes. So here's the application. that we used last time. Let's program it. Just make sure it's still working first. And get the serial monitor up. Yeah, it seems to be working, right? Alright, let's combine that code. First I'll add all of the schedule related code here. So there's my schedule stuff that we just created, and I'll add those new ports. And we'll do the setup for those ports as well. And that should get the IO ports set up. And now at the bottom here, I'm going to add all of the scheduling subroutines that we just created right at the bottom. So we'll have a new section here. There it is. So there's our little schedule that we created, scheduling subroutines that we created just as it was before. And now all we need to do is replace all of these. So if we look at each of these menus, so this is menu, submenu 3, I'm using this delay 2, right? Which is going to be in every one of these menus in the same place, even in the root menu as well, right? If we go up and have a look. So what we'll do is we're going to replace this with a wait, which will be which will also execute those background schedule tasks. 1, 2, 3, 4. That's it. All 4 of them. Alright, let's see if it'll compile. Alright, and we will download it. Oh, some activity. So the LEDs are they're flashing away. Let's get the menu up on the screen. And there it is. Now as we flicking around here, obviously we can flick around and those LED activity stays quite stable. Go into the submenu. And still flicking around, and still those LEDs are still sticking to their schedule. No problem whatsoever. Different menu. Flicking around, and still those background tasks are still working just fine. So we're not using any dedicated timers, no interrupts or anything crazy like that. This is very, very simple implementation. Something you can quite easily understand and do yourself. But the result is extremely high level, I would say. You get a very consistent real-time feeling of an interface. So there you have it. It's really as simple as that. Let me know what you think, or if you have any questions there in the comments. And if you have some sort of specific topic, something you want me to cover, for example, something you saw in the mini lathe control that you'd like to know how I did it or something like that, then of course drop me a comment in that regards too. Well, thanks so much for following along intently this far. I do hope to catch you in the next episode, so I'll see you then.